but researchers are still grappling with how to easily read the information held in these qubits and struggle with the short memory time, or coherence, of qubits, which is usually limited to microseconds or milliseconds. A team of researchers at the U.S. Department of Energy's DOE, Argonne National Laboratory and the University of Chicago have achieved two major breakthroughs to overcome these common challenges for quantum systems. They were able to read out their qubit on demand and then keep the quantum state intact for over 5 seconds, a new record for this class of devices. Additionally, the researchers' qubits are made from an easy-to-use material called silicon carbide, which is widely found in lightbulbs, electric vehicles and high-voltage electronics. It's uncommon to have quantum information preserved on these human timescales, said David Ozshalom, senior scientist at Argonne National Laboratory, director of the Q-Next Quantum Research Center, Liu Family Professor in Molecular Engineering and Physics at the University of Chicago, and Prince E. 5 seconds is long enough to send a light-speed signal to the moon and back. That's powerful if you're thinking about transmitting information from a qubit to someone via light. That light will still correctly reflect the qubit state even after it has circled the Earth almost 40 times, paving the way to make a distributed quantum internet. By creating a qubit system that can be made in common electronics, the researchers hope to open a new avenue for quantum innovation. This is exciting because it's easy to scale up, since we already know how to make useful devices with this material. The findings were published on February 2 in the journal Science Advances. 10,000 times more signal. The first breakthrough for the researchers was to make the silicon carbide qubits easier to read. Every computer needs a way to read information encoded into its bits. This procedure is challenging, however, because it requires detecting single particles of light called photons very efficiently. Instead, the researchers use carefully designed laser pulses to add a single electron to their qubit depending on its initial quantum state, either 0 or 1. By converting our fragile quantum state into stable electronic charges, we can measure our state much more easily. With this signal boost, we can get a reliable answer every time we check what state the qubit is in. This type of measurement is called single-shot readout, and with it, we can unlock a lot of useful quantum technologies. Armed with the single-shot readout method, the scientists could focus on making their quantum states last as long as possible, a notorious challenge for quantum technologies. The researchers grew highly purified samples of silicon carbide that reduced the background noise that tends to interfere with their qubit functioning. Then, by applying a series of microwave pulses to the qubit, they extended the amount of time that their qubits preserved their quantum information, a concept referred to as coherence. These pulses decouple the qubit from noise sources and errors by rapidly flipping the quantum state, said Chr. Each pulse is like hitting the undo button on our qubit, erasing any error that may have happened between pulses. The researchers think that even longer coherences should be possible. Extending coherence time has significant ramifications, such as how complex an operation a future quantum computer can handle or how small a signal a quantum sensor can detect. The ability to perform single-shot readout unlocks a new opportunity, using the light emitted from silicon carbide qubits to help develop a future quantum internet, Glenn said. We want to create a new generation of devices that are sensitive to single electrons, but that also host quantum states. This work was supported by the DOE Office of Basic Energy Sciences, Materials Science and Engineering Division, DOE National Quantum Information Science Research Centers, the National Science Foundation, Boeing, Swedish Research Council, Japan Society for the Promotion of Science, European Comissio. Writing contributed by Elena Glenn, Chris Anderson and Louise Lerner, Christopher P. Anderson, Elena O. Glenn, Cyrus Zeledin, Alexander Barasa, Yu Jin, E.G. Zhu, Christian Vorwerk, Alexander L. Crook, Hiroshi Abe, Jawad ul Hassan, Takeshi Oshima, Nguyen T. Sun, Julia Galli, David D. Oshalom. 5-second coherence of a single spin with single-shot readout in silicon carbide. Science Advances. 2022. 8.5, doi. 10. 1126, SCIADV. ABM 5912 DOE, Argonne National Laboratory. https://ift. tt. U5RMVYCKI. Accessed February 2, 2022. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.